All right, so now we're going to move into the thread local storage thing. This is going to have relevance to, it's basically an anti-debug technique or an anti-analyst technique. It's a malware trick that people use in order to get code to execute before you recognize that code is executing. So, just talking generally about threads. Actually, wish I would have went and stolen, yeah, and first of all, that slide's in the wrong spot. I think there's like a slide that was made for Veronica's class that talked about threads that I maybe should have stolen. But the point of threads is that, you know, we've been talking about, you know, there's this process here and there's this process there, and the operating system switches back and forth in terms of who's running right now. Threads are when you go even within a process and you say, I actually want to allow something, I want two things to be executing in the same process memory space. So it's the same memory. It's isolated. Task manager's threads are isolated from Notepad's threads. But within this thread space, potentially one thing, you know, if it didn't have multiple threads, if it was just a single threaded kind of thing, it would maybe try to go and read a file off of disk. And we know that reading stuff off of disk is extremely much slower than reading stuff from memory, right? You've got to go down to the physical hardware. It takes, you know, however many milliseconds or microseconds to get the data back. But for those microseconds, you could have been doing other work, right? And so what you want to have is you want to have two threads where one thread goes and tries to talk to the hard drive. And then it's sitting there waiting, and it says, OK, I know I'm going to be waiting when I call this talk to the hard drive. So go ahead and let this other code run. And it has its own context, and it'll continue doing something like updating the screen or something like that. So the point of multi-threading is that you don't want a program overall to get stuck talking to something that's slow, for instance, or waiting for packets on the network or anything like that. So you want to break it up the program so that the operating system says, I'm not just going to say Notepad can run and then Task Manager run. I can say Notepad thread 1 can run. And when Notepad thread 1 is, you know, says, hey, I'm stuck, I'm waiting on something, it'll yield and it'll say, the operating system says, oh, Notepad thread 1, you're done? OK, Notepad thread 2, you can run now. And then finally, when all of Notepad's threads run out of time, then it switches over to Process Explorer or whatever. All right, so that's the long-winded way of saying why we need threads. Beyond that, threads potentially need their own data storage. So they have their own context. And again, you maybe saw this in the, I'll just keep, you know, plugging her class and she'll keep plugging my class. Maybe in the malware class you saw something about a function called setThreadContext, which malware potentially uses. Thread context, you can think of it like a list of all the CPU registers for that particular thread. And the registers include the instruction pointer. So it says this thread is running right here right now, and this thread is running down here right now. So they've got their own state, like what do they have in their registers, where do they have their stack. And that's an independent thread context. So they've got their own context, but they potentially want their own sort of global data as well. They want to basically have some global that they set when they start running, but they want their global to be separate from the other threads' globals. Because when two threads are sharing the same global, they can be smashing each other's global, right? That's why we have mutual exclusion. You don't want two threads accessing the same data at different times and things like that. So they can say, I've got a global, but I don't want the other thread to access it. So this is what we call thread local storage. So it's saying, this is something local to me and my thread. This is for my availability and my thread only. And this is something I'm going to use independent of other threads, and I'll update it and so forth. So thread local storage, as you see it in Windows and Linux, it has the concept of like, here's some global data for my thread only. Where we differ is that Windows has the notion of thread local storage callbacks. And a callback means some function that'll get registered to be called. So I'm going to go into this now. So from the data directory, as normal, we're going to go to whatever index this is. And we're going to find the pointer to the thread local storage information. So from there, it points to this TLS directory. So if you hear something about a thread local storage directory or TLS directory, we're talking about the thing pointed to by the data directory. So within this, what we care about is that, you know, there's a start address of raw data and address of raw data. That's where the storage is going to be for the thread local storage. But what we really are interested in is this address of callbacks, because this is actually going to be an array of absolute virtual addresses saying, here's the function that I want to be called when when a new thread is started, for instance. So these are functions that kind of would happen at thread start in order to initialize data or something like that. right? So this is what I was just saying. Key thing is that all of these in thread local storage are absolute virtual addresses. They're not relative virtual addresses. And as I just said, these are the start and end of data. We're less concerned about the data. We're more concerned about the address of callbacks. And so, if I have it, okay. This is just an example in PEview. So we're saying in PEview, you would see something like this, image TLS directory. I'll show you in CFF Explorer in a second. This is the first order thing. This address of callbacks is an absolute virtual address. So we can probably guess that the base of this thing is hex 1,000,000 plus RVA of 11018. So this is the absolute virtual address of just an array where it's function pointer, function pointer, function pointer, null. And then it's done. And so the reason this matters is because these callbacks turn out to get executed before the address of entry point. So previously I told you way back in the optional header information, said address of entry point is the first place code starts. Set your breakpoint there if you're trying to debug something. That's where it's going to start. If there's TLS callbacks, those array of function pointers will get invoked, each one after the other, before the OS ever gets around to calling up to that address of entry point. And so what this means is if you're, an analyst and you're debugging something, you set, a breakpoint on address of entry point. Let's say you're kind of doing, static analysis. You're reading through the assembly code with IDA Pro. And so you're looking at the code at the address of entry point. You're looking at it and you're saying, this doesn't do anything. How does this malware actually run, right? It turns out they maybe will have moved their functionality to these callbacks. And so if you're sort of, let's say, junior analysts will generally not know about this. Medium analysts may or may not know about this. Medium experienced analysts. If they don't know about thread local storage, they won't be able to properly static analyze this. And they certainly won't be able to dynamically analyze it correctly because they'll set a breakpoint, they'll run to there, and the code will have already run off and talked over the network and stuff. And they're like, look, it has, it just hit my breakpoint. How did it talk over the network? If they've got, dynamic analysis going on in the background. So TLS callbacks is very important to be aware of if you're going to be doing any sort of malware analysis. Also interesting is that, so I've put a bunch of references that you should go read more about this because there's some crazy things that can happen with this. Amongst the crazy things is that if you, let's say you have a TLS callback, you go here, you look at the app's address of the app. Well, let me go to some data first before I go into that. All right, so here's what it looks like in PEview. Show you what it looks like in CFF Explorer. I went and made separate files for TLS callbacks. Actually, but I don't think it's going to have any TLS callbacks. By default, I add them in the code. Yeah, no TLS callbacks. So I got to start an example here. 7 or 8. All right, question. How many TLS callbacks does this binary contain? All right, I'm going to go open that in CFF Explorer. Question 8. Round 8, question 0. CFF Explorer, this gives you the same sort of first level cut of, here's the things we care about, start and end address. Well, you can see in this particular thing, start and end address are 0. So that need not necessarily be there. If it's sort of legitimate use, it's going to be using TLS callbacks for actual global data and stuff like that. But malware can just say, jump straight to the I want callbacks. So question is, how many callbacks are in this thing? Well, you've got an absolute virtual address. So now we're going to want to convert this basically to a file offset. And we can do that, convert AVA back to virtual address and virtual address back to file offset. I'm going to, let me hope that it's 32-bit. Yeah, 32-bit, so it's easier to do that in CFF Explorer, PEview. So I'm going to switch over to that. But the key point is that just like PEview, this will only give you this table. It won't tell you, here's the array. It won't show you, here's the array of callbacks. You got to go find that yourself. This is another one of those. The tools doesn't tell me, so I got to go find it myself. All right, so in PEview, rather, easier way to look at this, just because it's easier to convert relative addresses to virtual addresses. All right, so I have a nice little TLS section because I wanted to make easy code. So here's the stuff. It says the absolute virtual address where the array of callbacks is 40, 50, 18. Well, conveniently enough, I can see that I'm right up about the 40, 50, 14 right here with my stuff. So probably that callback array is in the data right after here, right? The next thing that would be up is 40, 50, 14. So if I go back to this raw view of things, 40, 50, 10, and then this would be 18 right here. And actually, here's a nice thing that I haven't showed you yet. You can actually change it to do D words instead of bytes at a time. That way you can get around some little endianness or issues if you're having those issues. So under view and raw data, you can change between bytes, words, and D words. Say again? Oh yeah, you're right. And then it's up here as well. Yep, good point. So 40, 50, 18 is where that array of callbacks is. So I'm going to go 40, 50, 10, 40, 50, 14, 40, 50, 18. All right, so I've got what looks like an absolute virtual address of a callback, absolute virtual address of a callback, it's the same one. Then I got a null terminator. So how many callbacks are in this binary? 2, yes. All right, and so this is how I have to actually figure that out. I have to go find wherever it was looking for, wherever it says in the headers, you know, here's the absolute virtual address of that table, and I got to go find that table and see how many entries there are before the null entry. All right, so the thing I wanted to tell you that's crazy is you can have one entry here, for instance, and then that one entry can go ahead and like hack this data in memory so that it adds a second entry. And then when it's done, that next entry will be added. So like if you're statically looking at this file and saying, yeah, that's got 2 callbacks, right? One of those callbacks could add a third callback. And if you're not actually looking at it with the debugger at runtime, you won't realize that there was some more code over here that got executed. So even just this static view of things is not the ground truth in terms of how many callbacks can potentially get invoked and where all the code will go. The nice thing is IDAPRO, the common reverse engineer tool for static analysis, does know about TLS callbacks. You can set it to break on TLS callback instead of entry point. So it will be able to catch these, and it should then catch as you walk through if you're using IDA's debugger. But that's TLS callbacks. That's all we're going to say about it pretty much. For your randomized game things, it's going to be pretty simple just because it was to make it easy on myself. I made a new section. I put the header information at the beginning, and then I tacked the array immediately after it. I could randomize this, put padding between them. I do need to randomize these callback addresses because you can see, OK, this is the absolute virtual address. I'm going to guess that this is relative address 1000. And so looking at the export address table, I've got a function at 1000, at 1020. So I'm going to later on randomize which callbacks it's using. This is just because this is about basically after round 6, that's about where stuff is not as good as it should be yet. So it's going to get sketchy here. All right. Any questions about TLS callbacks? Looking like that, plus an array. Only thing to know about them, so going back, just quick. Debug information, right? What do we care about debug information? Only thing, debug information, the only thing we care about is that there's going to be an address of raw data or a pointer to raw data, which will get us a nice string. So I think, I'm not actually sure whether yeah, maybe I did. Let me see what else is next, because I think, yeah, resources is next, and we don't quite have time to cover this beforehand. So let's say take 10 minutes to go ahead and play through the game, or just go do lunch and come back 10 minutes and play for the game. But we're going to start back again at 12:50, not 1 o'clock, because we got more material to get through. So ask any questions or play through the game. You do rounds 7 and 8. So 7 is debug information and relocation information. So 7 is debug and reload, and 8 is only TLS.